Professor, how are you?
Good evening. I went to wrong classroom. I'm wondering why no one get online. Okay, Adam first. 3.4, 16. Cecilia second. 3.45. Tanya 3.417. Great. Ryan 3.429. Jun E 3.43. Liz 3.419. Muhammad Zeman 3.313. Israel 4.119. All right, let's start. Adam, are you ready?
Yeah,
Walter?
I don't have presenting
Oh, yes.
permissions.
Yes, let me do that. Walter 3.35. Okay, Adam, you can go ahead right now.
So I was doing question 16, and I want to find the distance between 3, 0, and -1 to the plane 3x minus 2y plus 9z plus 1 equals 0 using the Lagrange multipliers. I'm not exactly sure how to say that. So
Lagrange.
Okay.
Right.
So I started off and I said let d be the distance between xyz and 301. And I solved for that using the distance formula. And then I said that I would let f equal d squared, which would just remove the square root of the distance formula. And I said g was equal to the equation of the plane. Then after that, I found the gradients of f and g, which came out here. And then after that, I used the Lagrange multipliers, and I set the gradient of f equal to lambda gradient g, and I solved through. And then once I got the what all of them were equal to, I subbed it into g, as you can see here, all of it where it was in terms of y, so I could then solve and find the point where you're supposed to evaluate f, and then I evaluated it with f at the point, which I found, which was 279 over 94, comma 1 over 47, comma negative 103 over 94. And then I evaluated it with distance, and I got that the answer was 1 over square root 94.
Okay, so Adam, let me ask you, why for this question you have to use Lagrange multiplier?
It asked it in the question. It said to use the Lagrange.
Oh, okay. All right. Is it possible you can explain to us what is Lagrange multiplier method?
I don't remember exactly because I read through the chapter last night and then did the question immediately, and I don't remember exactly how it works.
Okay, so first, think about it. We have first derivative test or second derivative test. Why we cannot do that? And why do we have to use Lagrange multiplier? First derivative test and second derivative test is for a function, a domain of the function is an open set. Because on the open set, we can differentiate, right? But this here, because it's working with a closed set. So that's why we have to use Lagrange multiplier. And the Lagrange multiplier is the same. Thinking about we use the word constraint, right, as a temporary domain. Think about a closed bounded set as a temporary domain of this function. Usually we look at as a level set of a function. Usually we're given a level set, and then from the level set, we can form a function of g. Then because we think about, once we have a g, we can think about the f as an object, g as an object, and the picture is these two objects intersect. So when these two objects intersect on the common points they're sharing, there's something which is a mathematician Lagrange found out. The gradient of those two are closely related with a scalar we call lambda. All right, and we call the lambda the scalar Lagrange multiplier. Lagrange is a mathematician, French mathematician. All right, thank you, Adam.
Thank you, Professor. Have a nice day.
You too. Next one is Jazilia 3.45.
Can you see my screen?
Yes.
So I'm doing a question 3.4, question 5, and the problem says f of x comma y is equal to x subject to x squared plus 2y squared equals 3. Find the extrema of subject to the given constraint. So the constraint in this problem was x squared plus 2y squared is equal to 3. So the first thing I did was find the partial derivative with respect to x of f, and is equal to lambda g of x. So the partial derivative with respect to x in the f of x comma y equation was just 1, and then we didn't have any y's to begin with, is equal to lambda, and the derivative in the g of x equation, which is basically our constraint, is 2x, and then we get 1 is equal to lambda 2x. I want to get x alone here, so I do 1 divided by lambda is equal to 2x, and then we also have to get rid of that 2. So I'm divided again, and I get x is equal to 1 over 2 lambda. And then I did the same thing for y. I did partial derivative with respect to y is equal to lambda derivative of the constraint. Partial derivative with respect to y of f is just 0 because we don't have y in this equation, and then x is just a constant. And then it's equal to lambda. The derivative of g of x is equal to 4y, which we have to then find y alone. So I do 0 divided by lambda, which is equal to 4y. And I get 0 is equal to 4y. 0 divided by 4 is just 0, so we get y is equal to 0. And then I had to find what is lambda in this case. So what I did was just plug back into our constraint. So x squared plus 2y squared is equal to 3. For x, we got 1 over 2 lambda. So now I have 1 over 2 lambda squared. And then for y, it's just 0. So plus 2 times 0 squared is equal to 3. Anything times 0 is 0. And then I multiplied 1 over 2 lambda times 1 over 2 lambda to get 1 over 4 lambda squared is equal to 3. And then I brought our denominator up on the left side. So I did 4 lambda squared times 3, which gives 1 is equal to 12 lambda squared. Again, we're trying to solve for lambda here, so I have to divide that 12 by 1, and I get 1 over 12 is equal to lambda squared. I have to get rid of that square root there. I have to get rid of the square there, so I do the square root of 1 over 12 and the square root of lambda squared, which gives lambda is equal to plus or minus 1 over 2 radical 3. And then I had to find x and y, getting rid of the lambda here. So y is just 0 still because we didn't have lambda in the first place over there. And x is equal to 1 over 2 times negative 1 over 2 radical 3. And then we get negative radical 3 when we multiply that out. And then x is equal to 1 over 2 times 1 over 2 radical 3, which is equal to radical 3. And then our points become negative radical 3 and 0, since x was negative radical 3 and y is 0. And then we get radical 3 and 0, since radical 3 was x and y was 0. And then I compare these two values so I can see that the local minimum was radical 3 comma 0 and the local maximum was radical 3 comma, negative radical 3 comma 0 for the local minimum and radical 3 comma 0 for the local maximum.
Nice. All right. Tanya next, 3.417. Then Ryan, 29. GE, 3.43.
So question 17 is asking to find the maximum and minimum values attained by f xyz is equal to xyz on the unit bowl x squared plus y squared plus z squared is less than or equal to 1. So for here, I use the Lagrange multiplier method because I realized it's a closed set and like first derivative test that wouldn't work here. So the Lagrange multiplier is the gradient f is equal to lambda times the gradient g. The gradient f is the partial f is that formula. I just wrote it again just to have it clear. And then I did the partial of f with respect to x, and I got yz. The partial of f with respect to y, I got xz, and the partial of f with respect to z, I got xy. Then I did the partial of g with respect to x, and I got 2x. The partial of g with respect to y, I got 2y. And the partial of z with respect to z, I got 2z. Then I did, I used the Lagrange multiplier method. So then I did yz is equal to lambda 2x. So normally that you would solve for x, but here I solved for lambda because I realized if I solve for x, it's going to be very complicated and it'll have there'll be 4 variables. So I realized if I make them all equal to lambda, then it'll just make it easier. So for solving for lambda, I got yz over 2x. Then I did also for the next one, xz equals to lambda 2y. And then I got xz over 2y equals to lambda. And then xy equals to lambda 2z. And I got xy over 2z equals to lambda. So now that since that they're all equal to lambda, I could take 2 equations and make them equal to each other and then solve for one variable. So I took the first 2 equations and I did yz over 2x equals to xz over 2y. And then I divided by z, and then I cross multiplied, and I got y squared equals to x squared. Then I did the same with the second and the third equation, which was equal to lambda. So I did xz over 2y equals to xy over 2z. And then I divided by x and I cross multiplied and I got z squared equals to y squared. So since we have x squared equals to y squared, since x squared equals to y squared, I plugged that into the g. So instead of x squared, I put y squared, so then y squared plus y squared. And then instead of z squared, I also put y squared. So it became y squared plus y squared plus y squared equals to 1. And then I got 3y squared. And then y squared equals to 1 over 3. Square that, and I got y is equal to plus minus rad 3 over 3. And then I plugged in 1 over 3, which was what y squared is, and I plug that in to get what x squared is, and x is also equal to plus minus rad 3 over 3. And then to find z squared, I plugged in 1 over 3, and I got z is also equal to plus minus rad 3 over 3. And then I took these x, y, and z, and I plugged that into the x, y, z. And I got rad 3 over 9, also same as like 1 over rad 3, rad 3. And then I did the negative of it, of negative rad 3 over 3. And then I got negative rad 3 over 9, same as negative 1 over 3 rad 3. And then 1 over 3 rad 3 is the local maximum, and negative 1 over 3 rad 3 is the local minimum.
All right, Tanya. Thank you.
No problem.
Let me mute Jazelia. All right. So next one, Ryan, 3.429. Then Junyi, then Liz.
So my question basically asks for a parcel, a rectangular box that's constrained so that the length plus twice the width plus twice the height is less than or equal to 108. Now, ideally, because we have a constraint, we use a Lagrange multiplier setup. And the inequality can sort of get a bit complicated. So because it must be less than or equal to 108, I decided to simplify that to equals 108 because the largest volume, which is what we're optimizing, length times width times height, will definitely come out of the largest possible box. So it should be 108. So because of that, I had my original function that I'm optimizing. I set that to f, so length times width times height, and my g, which is my constraint, I set that to length plus 2 times width plus 2 times height minus 108. So I basically just got rid of the inequality. And I took the partial derivatives with respect to each variable of both functions, and that basically just gave me the gradient. So partial derivative of f with respect to L is just width times height, because L is basically just x, and that becomes just a constant, just 1. So, and then basically the same here, we get rid of the W, and here we get rid of the H. And for G, for the partial derivatives, L just becomes 1, W just becomes 2, and H just becomes 2. And so setting them all basically equal to each other, but multiplying these terms by lambda, there is lambda equals width times height, 2 lambda equals length times height, and 2 lambda equals length times width. And that's basically a system of equations. We have lambda here. I never really solve for it because, I mean, there's really only going to be one critical point, and that is the maximum. So I don't really have to classify it as anything. So I basically just plugged in for lambda, and I got length equals 2 times the width. And then I plugged in again for lambda, and I got length equals 2 times the height. And then since they're both equal to length, just 2 times the width equals 2 times the height, and width equals height. So that's the most optimal setup. So plugging those back into our constraint function, I basically got that the maximum point will be at width equals 18. And I basically just solve from there because we have basically length equals 2 times width and height equals width. So I could just convert that all into width. And so I got 36 times 18 times 18 equals 11,664 inches cubed, which is the maximum volume that we could get. And if you wanted a critical point, that would be specifically 36, 18, 18.
Very nice. Thank you, Ryan. Very clear.
Thank you.
Junyi, 3.3, then Liz, then Muhammad Zaman.
1 second, please. Okay, so basically this is the question to that function of f subject to the function of g, that which is like x minus y plus c and x squared plus y squared plus z squared equal to 2. I use the gradient of f x y z equal to
Hold on 1 second. Hold
uh-huh.
on just 1 second. Okay, right. X squared plus y squared plus z squared equal to 2 is a level set. Out of this level set, you can manufacture function g, but you cannot, keep going with this equal sign. Function g equals to 2, you are doomed, right? That's just a constant.
Okay.
Okay,
so I
okay.
don't need to put the
Actually,
equal to 0 for that.
No, hold on 1 second. Actually, I can write on yours.
Okay.
Just ignore this part, okay?
Okay.
Ignore this part. Because if your function g equals to 2, what's the gradient? 0. And when g gradient 0, you cannot do anything anymore. So this is given to you, x squared plus y squared plus z squared equals to 2 is given to you as a level set. Out of this level set, you manufacture function g as x squared plus y squared plus z squared. Or if you want to involve 2, you would see minus 2. You would change equal sign to minus 2.
Okay.
You can make a function g of x comma y comma z equals to x squared plus y squared plus z squared minus 2. Or simply, for me, I just make g equals to x squared plus y squared plus z squared. Because when you take a partial, when you take a gradient of g, this 2 doesn't contribute to anything. It's 0.
Mm-hmm.
Make sense?
Yes. Thank you, Professor.
All right. You're welcome. Keep going.
So we take the first. I take the first derivative of function f. It got 1, -1, and 1, and the lambda the gradient g go to the lambda times the 2x, 2y, and 2z. So I set up the equations, which is the 1 equal to the lambda 2x, -1 equal to the lambda 2y, 1 equal to the lambda 2z. So which it shows like the x equal to z, which is 1 over 2 lambda. And also x could be the negative y, which is the y equal to -1 to 1 over 2 lambda. And also the equation that given out x squared plus y squared plus z squared equal to 2. So I plugged in the numbers, which is the 1 over 2 lambda squared plus the -1 over 2 lambda squared plus 1 over 2 lambda squared equal to 2. And then I got the 3 over 4 lambda squared equal to 2. And then I do the division, which is I got the 3 over 8 equal to the lambda squared. I put the radical and the lambda equal to plus and minus radical 3 over 8. And then I plug in back the number to the x equation. Says x equal to 1 over 2 lambda equal to 1 over 2 plus and minus radical 3 over 8. And then I factor out the radical 8 to eliminate the 2. Then the final answer I got plus and minus radical 2 or 3. So the maximum numbers will be radical 2 or 3 times the 1 comma -1 comma 1. And the minimum will be the negative radical 2 or 3 times the 1 comma -1 and 1.
All right. Nice.
Thank
So
you.
because I can write on your paper, I would like to write this one. So usually when we form system of equations, we give a big parenthesis to indicate this is a system of equations you're solving. There are many ways, there are different ways to solve system of equations. You don't really have to solve for lambda, but sometimes you have to, all right? Just a different ways of solving it. Very nice. All right, that's Junyi, Liz, 3.419. Then Muhammad. Les? Are you talking? I cannot hear you. Okay, your work is up, but I cannot hear your voice. Okay.
Can you hear me now?
Yes.
Professor?
Yes. You cannot hear me? Let me type. Yes, Les. You cannot
Okay.
hear me?
So this is 3.4, number 19. It's two part, A and B. So for A, we want to find three numbers whose product is 27 and the sum is minimal. So we're gonna consider three numbers x, y, and z with function f of x, y, z equals to x plus y plus z, and the product will be x times y times z equals to 27. So we know that the sum is s equals to x plus y plus z. S equals to x plus y plus 27 over x times y. So we get this from the product, which when we try to solve for x, that's for z, that give us 27 over xy. So we take this and we replace it into the sum. Now we take the differential with respect to x, and next we do with respect to y. So partial derivative with respect to x give us 1 minus 27 divided by x squared times y. And the partial derivative with respect to y give us 1 minus 27 divided by x times y squared. So we take this the partial derivative with respect to x, and then we set it equals to 0. Then we solve for y. We end up having y equals to 27 over x squared. We substitute this value of y into the partial derivative with respect to y. So this gives us x times y squared minus 27 equals to 0. And x times 27 over x squared square equals to 27. This give us x cubed is equals to 27, and when we do cube root of 27, we find that x is equals to 3. So we can conclude that the three numbers whose product is 27 and the sum is minimal are 3, 3, and 3. For part B, we need to find three numbers whose sum is 27 this time and the product is maximal. We consider three numbers x, y, and z, and the function f of x or y z equals to x times y times z, and the sum is x plus y plus z equals to 27. We know that the product P is x times y times z. So we kind of solve for z into the sum equation that we had, and z the new value for z is now 27 minus x minus y, which we replace into the product. That's why the new value of p is now 27xy minus x squared y minus xy squared. We take differential with respect to x and y. So partial derivative with respect to y give us 27y minus 2xy minus y squared. And the partial derivative with respect to y give us 27x minus x squared minus 2xy. We substitute partial derivative with respect to x equals to 0. Then we have 27y minus 2xy minus y squared equals to 0. And when we solve that, give us y equals to 27 minus 2x. We substitute this value of y into the expression into the partial derivative with respect to y. And that's give us 27x minus x squared minus 2x, parenthesis 27 minus 2x, close parenthesis, equals to 0. When we simplify, we end up having 3x squared equals 27x. That gives us x equals to 9. So the value of y is y equals to 27 minus 2x. We replace the value we find for x, and that gives us y equals as well to 9. Now the value of z using the sum equation, we replace x and y by their values so we can find z. So 9 plus 9 plus z equals to 27. We end up having z equals to 9. So the three numbers whose sum is 27 and the numbers whose product is maximum are 9, 9, and 9.
All right, Liz. There's one more solution. I'm not sure if it is. Look at this equation. 3x squared equals to 27x. There's one more solution for this. What else x can be
Professor?
to make this true? Can you hear me? You cannot hear me? Can anybody else hear me?
Yes.
Liz, only you cannot hear me. I don't know what's going on. Just read, I type in the chat. There's one more solution for equation 3x squared equals 27x. Can I type in this? X equals 0, right? So just
Yes.
double check. Just double check when x equals 0, what happens?
When x equals 0,
right.
x equals 0, so y equals 27.
Okay. Okay, just double check this. All right. Okay, thank you, Liz. So next one, Mohammed Zeman, 3.313.
Yes,
Then
Professor.
Israel.
Yes, sorry, go ahead.
All right. Israel.
Oh, sorry. Is it my turn?
Oh, yeah, it's your turn, right? Oh, no, hold on a second. No, Mohammed Zeman's turn. Sorry.
It's okay.
Israel, Walter, Gabriel, Dayeli, Josephine.
Okay. Yes. Professor, do you see the screen?
Not yet. Yes, now.
Okay. So I did section 3.3 yesterday. I couldn't present this. It was question number 13. So it was someone already presented this in class, so I'm just going to do it quickly. I'm going to explain everything to show what I understood. So we had to find the critical points. That's the first step.
Hold on one second.
Yeah.
Hold on one second. You're seeing someone already presented?
No. Someone presented a similar question, but not this one.
Oh, okay. Okay, I got it. Go ahead.
Yeah, so they found the critical points and all this stuff as well. So the first step is finding the critical points, and then the second step following this step is determining if those critical points that we find are local maxima, minima, or saddle points. So the function that we're using is right here. f of x and y equals x times y plus 1 over x plus 1 over y. So I wrote some notes for us. I'm going to go over them later on. So the first step, using this function, we have to find the first partial derivatives. So we have to find them separately. We have to find it in terms of x and then in terms of y. So we can use them separately to find the values of x and y. So first, I took the derivative of x and I got y minus, in respect to x, so d over dx, I got y minus 1 over x squared, and when I took it in terms of y, I got x minus 1 over y.
Please hold on one second.
Yeah.
Hold on one second. Okay, so
So
we're in a world of,
yeah.
so f goes from 2 space to 1 space. It's not a single variable calculus.
Yeah.
You have 2 variables. So when we deal with 2 variables, we don't use this d, lowercase d anymore. What else we use? We use a
Oh, the
specific.
sign. Yeah, I didn't put that sign to make it easy for
We
me.
use we call partial.
Yes.
Partial f.
Partial derivative sign.
Yeah, partial f, partial x.
Yeah.
Alright.
So I just made it easier for myself to understand. So let me quickly explain this
But
how I
when you
got
present,
this one of
but
them.
when you present, you have to use the same language. Just like when you speak English, I have to speak English, so we can understand each other.
Yes, I got you, Professor. So more, yeah.
Use the sign of a partial f, partial x.
Okay, I got you. So I'll do that next time. So let me just quickly explain how I got from here to here, just for one of them, because I also did the second partial derivatives. To not take too much time, I'm just going to quickly explain. So x and y, so what happens with the x? So the derivative of x would be just 1. So that cancels out the 1. We don't put the 1. So we just take the y. So the first partial derivative in terms of x of this first part, x and y, would be just y. Then of plus 1 over x would be, so we would have to use the power rule, and I did that. I didn't put it here, the calculations. The power rule, it basically gives us negative 1 over x squared. And then since the third part, since it's in terms of x, we treat this as a constant, 1 over y, so we don't put that in the first partial derivative in terms of x. So we treat this, the third part of the equation, as a constant. And the same thing goes for the first partial derivative in terms of y. So when I got the values, I used one of the equation and I plugged in the second into the first one. So for example, I used 1 over x squared. This equation, I plugged in what x equals 1 over y squared. I simplified that, and you can see the simplification right here, and I set it equal to 0. You have to set it equal to 0 to find what y equals. So when you set it equal to 0, you just simplify it, and at last I got y to the third equals 1, and then y was equal to 1. Then I used you can use either formula again. I used the second one, x equals 1 over y squared. I plugged in what I got for y. So here is y, which is 1. So 1 over 1 squared is basically 1. So y and x, so x and y are 1 and 1. So these are our final critical points. Now we have to determine, the question asks us to determine if it's a local maximum, minimum, or saddle points. So to go into that, we have to do the partial derivative again. It's called the second partial derivative. But now there's an extra step. We also have to do it in terms of x and y both. So we take the partial derivative again, second time. So we take the derivative of these two again. And I got 2 over x to the third. And in terms of y, I got 2
Second
over y to
partial
the
in
third.
x, right?
Yeah.
So partial f. So this f x read as second partial in x component.
So
F,
second
y,
partial
second
derivative in terms of x, yes.
right? Then mixed partial. All right, yeah,
Yeah,
keep going.
and then the mixed partial, which was 1, because this was a whole different game. It simplified to 1 minus 0, and it basically came to 1. Then I used the formula given, which is d equals fxs. I told you I put some notes. So this basically says that if d is less than 0, the critical points are saddle points. If it's greater than 0, they have to be either a min or a max. So, and then further on, this is f. So this is this right here. This is the second partial derivative in terms of x. So if that's greater than 0, it's a minimum, 100%. If it's less than 0, it's a max. So now we go put the values into the formula. So I use the formulas for example, the second partial derivative in terms of x, 2 over x to the third. I use the critical points I treated this as x and y. So I plugged in the first value for the x, and I simplified in terms of fxx, meaning the second partial derivative in terms of x. So I didn't need a formula. I needed a specific value, which was 2. I did the same thing for in terms of y. I got second partial derivative in terms of y. I got 2 again. Then I already had f in terms of x and y. The second partial derivative is 1. So I just plugged in the formula, the values. So 2 for this, 2 for fyy, minus 1 for fxy squared. It gave me 3. So d is greater than 0, so it has to be a min or max. There's no saddle points at all. So then the notes say that if the second partial derivative in terms of x is greater than 0, it's a min. If it's less than 0, it's max. So here we can see it's greater than 0. So it has to be a minimum. So the final answer of the whole question is that yes, it has critical points. There's no saddle points, and the minimum is at the critical points 1 and 1. That's it.
Very nice. Thank you. Just watch out the language you're using. Okay, Israel, 4.119, then Walter, then Gabriel, Dayeli, Josephine.
Okay. Oh, I forgot to. Let's see.
Hi,
Okay.
wait, hi, Professor Nisfield. Do you mind if I present quickly just because I need to leave?
I mean, I wouldn't be opposed, if anything.
Oh, okay, yeah.
Yeah.
Okay,
so
thank you so much. Sorry, I just have to go somewhere. Okay. I did question 1 and 3.4. So the question was f of x of y is equal to x squared plus 3y squared, and is to find the maximum value subject to the constraint x squared plus y squared is equal to 1. So the x squared plus y squared, I didn't label it here, but that would be our g. So taking gradient f, or I just did partial f partial x is equal, actually ignore that part because I ended up doing instead setting that equal to 0. So I did lambda times partial g partial x minus partial f partial x, and doing that. So partial g partial x was 2x, and then partial f partial x was also 2x. So I got lambda times.
Just hold on. Oh, okay, go ahead. Keep going.
Okay, so I got lambda times 2x minus 2x is equal to 0. Factoring out the 2x, I got then 2x times lambda minus 1. So I got x is equal to 0, and then lambda is equal to 1. Is okay so far?
Yes.
Okay. And then I did partial f, partial y. Well, lambda times partial g, partial y minus partial f, partial y is equal to 0. So here, partial f partial y would be 6y, and since it's being subtracted, it would be negative, so I wrote that in the front. And then partial g partial y is 2y. So then here I factored out negative 2y. So I got negative 2y times 3 minus lambda. So I got lambda is equal to 3 and y is equal to 0. So going, if x is equal to 0 and then plugging that into our constraint, then y is equal to positive or negative 1. And then, so you have 2.01 and then 0, negative 1. And plugging that into our f, you get that for both of them 3. And then if y is 0, then we get x is either positive or negative 1. So our points would be 1, 0, and negative 1, 0. And then plugging that into f, we get 1, 1. So for part A, the max value would be 3 and the min value would be 1. And then for part B, I don't have it written down, but it's essentially all the same steps, except the constraint is going to be x squared plus y squared is less than or equal to 1. So since it's less than or equal to 1, we have the possibility of a 0.00. So then that would change the min value to 0, but the max value would still be 3.
That's not similar to this one. Part B, if part B x squared is x squared plus y squared less than or equal to 1, is totally different from A.
Oh, okay.
It's totally different. But before that, I want to ask you, you have a lambda equals 1, lambda equals 3 as a solution of your system equation, but you didn't use it. You didn't use lambda equals 1, lambda equals 3. Can you explain on that?
Yeah, I was honestly going to ask that because that's what confused me in the beginning, was that like when I did the first part, if you get lambda is equal to 1, then when you put like if it's unlike the other ones where you like then solve for x, yeah, I'm not really sure.
Right, because I was about to ask you a question, 2x equals lambda 2x, lambda equals 1, but then you did something else. So what is the difference between 2x equals lambda 2x and you see the bottom? On the bottom, you erase something. You're saying 0 equals lambda 2x minus 2x.
What's the difference?
What are you doing? Yeah, what is the difference?
So the only difference is that instead of, it's basically minusing the partial f partial x to the other side and setting it equal to 0, because I saw that in the textbook as a way to find the critical point.
Exactly.
So that's why,
because the first one, when you see 2x equals lambda 2x, then you conclude lambda equals 1, you're missing the solution x equals to 0. So this part, you should erase this part. You should erase, let's see, under little letter A, lambda equals 1, lambda equals 3. That's not right.
Yeah, that's, I said ignore that part. I realized that was wrong, but I don't have like, I can't.
Okay.
Yeah.
I see, I got it. So that's fine. Then your B part, can you show us your B part? Because B is totally different from A.
I actually don't have B with me.
Okay, remember someone already asked this question. If you choose to present one question, you have to present the whole part. If you have A, B, C, you have to show the whole part. So this one, I can only give you half credit for it. Because less than or equal to 1 is different from equals 1.
Yeah, I wasn't, I'm not, like, how does it, can you explain how it changes it? Because I wasn't sure how it would change, like, those steps.
Okay, equal x squared plus y squared equals to 1 is what kind of set? Is it an open set, closed set? Is it open, closed set?
Would it be closed because it's equal to 1?
Exactly. It's the boundary of the disk. But when you have x squared plus y squared less than or equal to 1, you have two things.
Okay.
Were you in class yesterday?
Yes, I was, but I need to re-go over it.
Yeah, I mentioned a couple of times already, right? Because when you have x squared plus y squared less than 1, that's not open set. So less than or equal to 1 is a closed and bounded set, which has two parts. It has an open set, which we call interior points, and then we have boundary points. Boundary points are x squared plus y squared equals to 1.
Okay.
Okay.
Got it.
All right. Thank you, Josephine. So Israel, back to you.
Okay. Drive. Hey. So I'll be presenting 4.1.19, and the question asks that show that if the acceleration of an object is always perpendicular to the velocity, then the speed of the object is constant. So to quickly give some context from what we're going to learn in chapter 4 to help with this problem is that acceleration is equal to the derivative of the velocity vector, which is the double derivative of the initial vector, as well as the dot product rule, which states that the d of dt of any the dot product of any two vectors will equal to the derivative of the first vector times times the second vector plus the derivative of the second vector dot the first vector. And also from past chapters to talk about is that the velocity vector, finding the magnitude of the velocity vector gives us the speed, and any squaring any magnitude will give us the dot product of the vector times the dot product of the vector of itself. As well as, whenever we say that the dot product of any two things is equal to 0, they're perpendicular. So with all that in mind, what we do is we square the magnitude of the velocity vector, which gives us itself dot itself, while taking the derivative. So that means we can take the dot product rule, which gives us the derivative of the velocity vector dot the velocity vector plus another one of it, which makes 2 times the derivative of the velocity vector dot the velocity vector, which means we can have the acceleration vector dotting with the velocity vector. Because of what the question's asking is that to show that the acceleration of the vector, or not to show that, but it's stated that the acceleration vector is perpendicular to the velocity vector. This means that the dot product of those two is 0, meaning this entire thing is 0. So this proves that the speed is a constant because of the fact that the derivative of said speed is 0, because as it should be.
Okay. All right. Thank you, Israel. Walter, next one, 3.35. Then Gabriel, 3.413. Dayeli, 4.11.
Okay, so my question was section 3.3, question 5, and it was similar to Mohammed's question in the sense that we are looking for the critical points and determining if those critical points are a local minimum, maximum, or saddle point. And so to start off, in order to look for critical points, we need to look for the partial derivative of the function in terms of x and y. And so the partial derivative in terms of x, I got 2xe to the power of 1 plus x squared minus y squared. And for in terms of y, I got negative 2y e to the power of 1 plus x squared minus y squared. And I set both of these partial derivatives into to 0 since we're looking for its critical point. And I noted that since e cannot equal to 0, the only possible way for these partial derivatives to equal to 0 is if the variable in their coefficient are set equal to 0. With this in mind, basically we're saying that there only exists one critical point, and it's set at the origin. And then for to determine whether this is a relative minimum, maximum, or saddle point, we need to use the second partial derivative to help us find its discriminant. And so the discriminant is equation on the bottom, where we use this second partial derivative in terms of x, the second partial derivative in terms of y, and the second partial derivative in terms of x and y. And if the determinant is less than 0, it's a saddle point, and if it's greater than 0, it could be either a relative minimum, local minimum, or a local maximum. So for the second partial derivative at the origin in terms of x, I got a value of 2e. The second partial derivative of the function in terms of y at the origin, I got a value of negative 2e. And the second partial derivative of the function in terms of x and y at the origin, it gave me a value of 0. And so I substituted these values into the equation at the bottom, and I got a value of negative 40 squared. And since this value is less than 0, it's going to conclude that this critical point is a saddle point.
Very nice. All right. Thank you. Gabriel?
Okay, I did number 13 of section 4 of chapter 3, and sorry, the question's just like on the side because I couldn't fit it, but it's basically the same thing as what a lot of people are presenting. You're given a function that is defined on a unit disk, and you're also given that equation, and then you're asked to use the Lagrange multipliers to find the maximum and minimum points, and then from there find the absolute minimum and maximum values. And then back from section 3 of this chapter, we know that, like, for starters, that this entire function has an absolute maximum and minimum from theorem 7, since it's a closed figure or plane. But yeah, just jumping right in, basically what I did was I separated sorry, I don't know why I'm blanking, but I separated the D equation into U and the derivative of U, which is basically like the interior part and the boundary. And then I found the partial derivative of x and y at 0. And then I just got x is equal to 0 and y is equal to 0. So then that was my critical point, the origin. And there's a similar example in the book, and they ended up finding the discriminant at the end. But I just found it right away, so I did that. I just found the rest of the partial derivatives that I needed, and then I found the discriminant to be 2, which is greater than 0, which makes the origin a minimum point based on the second derivative test from section 3. And then so I moved on to using theorem 8, or like the method of Lagrange multipliers, on the right. And then I just found the derivative, and I used the formula, which is just the same thing, the gradient of f is equal to lambda gradient of g, and then I evaluated it both at x and at y, and then since both were like lambda equal to something, I equated both lambdas, and then I got y, which is plus minus x. So then I went back to the level curve that I got from the beginning, or like the partial u, and then I put it in there, and then x squared plus y squared equals 1 could basically be written into y squared plus y squared equals 1, and then since it's all the same when you square it, and then I found plus and minus 1 over the square root of 2, and then I got 4 possibilities, and since we already have a minimum point, we're basically looking for the maximum point. So I tried these all out by evaluating them with the very original equation, the x squared plus xy plus y squared, and the ones with the biggest answer were -1 over square root of 2, -1 square root of 2, and +1 over square root of 2, +1 over square root of 2. And then to find the absolute minimum and absolute maximum, you just do the same thing. You just evaluate your points at the original function, and that's what I got. So these points, you could say that, one second. You could say that the absolute maximum of f on D is 3 over 2 at the points -1 over square root of 2, -1 square root of 2, and 1 square root of 2, 1 square root of 2. And then the same goes for the absolute minimum. It is the value of f on D as it occurs at the origin. Sorry, that was just like a lot. I just like got jumbled up in my words.
It's okay. It's good. It's good. Very detailed. Thank you, Gabrielle.
Thank you.
And Dayeli, next, and the last one, 4.11.
All right, I'm gonna share my screen really quick. Just give it a few seconds. It's uploading. It's loading. Oh, that is not mine. What the?
Wait, it's up.
No, that's not my work. Sorry. Somehow I can see everyone's work here.
It disappeared.
I don't know why it's doing that. Okay. Here we go. Alright. Okay, so can you guys see my screen?
Yep.
Alright, so question 1 from section 1.1 for 1.4.1 is asking us to find the velocity and the acceleration, and then the equation of the tangent line for each of the following function. I don't know if you remember from section 2.4 about the tangent line equation is one of the key factors that we're going to be using here to help us to solve this problem. So I started by finding the first derivative, which gives us the velocity vector. That is something that we learn in first variable calculus. And we are giving a let me start over. So we're given the function r of t equals cosine of t times I plus sine of 2t, and then at t equals 0. I started by finding the first derivative, which gives us the velocity vector, and then I evaluated at t equals 0, and I ended up with it being 2j, it equals to 2j. And then to find the acceleration vector, we gotta take the second derivative of our function, which is equal to negative cosine of t times I minus 4 sine times 2 to tj. That is our acceleration vector. And we evaluate it at t equals 0, which gives us negative I. Now,
if we remember from section 2.4 about the tangent line equation, it's basically right, this equation right here. So now in this chapter, a key factor that they mention is that v equals to c prime of t. In this case is our velocity vector, this one right here. So then this would be equal to v right here, which I'm using in the function right there. So I'm just evaluating r equals 0 of my equation right here. I'm just plugging in 0. So I get 1, 0. And then for my v of 0, which is my first derivative of r, which was when I plug that in, when I evaluate it as 0, I get 0 and 2. So I'm just plugging it in to the tangent line equation, this one right here, which I ended up with I plus 2s j.
All right. I guess everyone has presented. Anyone has any questions? Anyone has any questions? If not, it's my turn. Somehow, people are very busy today. There are only 9 of us left here. So we're finishing chapter 3. So I'm going to address a little bit of 3.5, the implicit function theorem, which is not going to be on the exam. All right, then tomorrow I'm going to talk about starting chapter 4. Implicit function theorem. Let's just recall from single variable calculus, right? If all the condition holds, we will have this implicit function theorem, which says the inverse of function of f, the derivative of the inverse function of f, of course, inverse takes a y as input, right, equals to 1 over the derivative of f, right? So the condition is if y equals f of x is the first level differentiable and the derivative cannot be 0, then locally near this such next point, we can solve for x to give the inverse function. Because sometimes the inverse function is x if we can find the inverse of the function, right? Otherwise, we wouldn't be able to talk about it. If we can find the inverse of f, right, that means x equals to inverse and takes a y as input. So we have this condition. Sometimes we find the derivative of the inverse function of f at a point is difficult, so we may use this method, so which is 1 over derivative of f, or evaluate it at the point. Right. Well, we can write this way: dx over dy equals 1 over dy over dx. This is obvious, right? Right, when the condition holds. So similarly, so this word invertible means the inverse function exists. A lot of times we cannot find the inverse function for a function, but certain times we can. All right, so the idea is the same. So we have this, right? So this is the previous conditions. You see, the idea is the same. Okay. So derivative of g equals to negative 1 over partial f partial z, what takes x comma z as the input. And we know this is a matrix, right? We know that the matrix has all entries, depends on the size of domain and the size of a codomain. Okay, general implicit function theorem. So it's saying we attempt to solve m equations for m variables, z1 up to zm, right? So we have f goes from an n space, real value function, right? And to m space, right? Think about each component is real value function. But this f, so this is f1 first component, f2, so on and so forth. It just didn't say here, but just imagine your head. F is self. Think about the f is self, no 1, no 2. Going from n space to m space. And we're trying to solve f1 takes all this, how many n plus m variables. So this f1, the domain of f1 is in n plus m space. So this equals 0, f2, this equals 0, so on and so forth. So we have m equations. And the partial f partial z cannot be 0. Okay, maybe let's go back to 11 a little bit so you can see the precondition of setting up. Okay, or f from n plus 1 space. So f itself is a real value function from n plus 1 space to 1 space. Okay, so what do? We do this, right? So f takes x, then one more direction, z direction, and x is n space vector. Then at this point we have function value equals 0, but we require the derivative, the partials in z direction is not 0. Okay, so this is a precondition. Or basically you can think f as a component, as this function, right? You have g function takes z. What is this? X comma g of x is a graph, right? A function, the graph of g. So f just takes one more dimension. F considers x in n space vector plus the function value of x. So we use the same setup for general implicit function theorem. So we have this m. So we require this not equal to 0. And this is using this delta notation, saying, you know, one more thing cannot be 0. What is this? This is the n by n matrix, come from all those components. Okay, so this is general implicit function theorem. We've seen this m by m matrix is not 0. The determinant, all right? The determinant of this m by m matrix is not 0. The near point x naught z naught equation here one, here. These M equations. Define unique smooth functions. Smooth means continuous and differentiable, specifically for differentiable. So each zi is thinking as ki as a function of n variables. Then their derivatives may be computed by implicit differentiation. All right, let's see this example. So we want to show near the point, like in 4 dimensions, we can solve these equations. So given these 2 equations, and we want to show we can use this. So this point is a unique solution for that, for u, v as function of x and y. And then compute partial u, partial x, because we have u, v, compute partial u, partial x at the point 1, 1. Okay. So first we check if it's possible to solve. So let's form an equation f1 xy uv, or u and v are functions in terms of xy, right? Think about this as x1, this as x2, this as z1, this as z2 in the formula. Okay. Then we form f1 as this, right? We just remember equals 0, f1, f2, up to fm equals 0. So we just move 2 to the other side. So we make this xu plus yvu square minus 2 equals 0. Similarly for f2, right, for the second equation. And then we calculate the determinant, partial f1, partial u, partial f1, partial v, partial f2, partial u, partial f2, partial v. Right, in the formula just use z. So those z's, z1 up to zm. Then we do that, so we get this 2 by 2 matrix. Then we want to evaluate at x, y, u, v equals 1, 1, 1, 1. So we get a determinant to be 9. Because the determinant is not 0, so we can solve the system of equations by using implicit function theorem. So partial u, partial x, right? We differentiate that, we get this equation. We simplify the second equation, we get this one, right? Then again, evaluate at 1, 1, 1, 1, so we get these 2 equations, right? 2 equations with 2 variables we can solve. So solving partial u, partial x, then, well, you can use a different method, right? So partial u, partial x, partial u, partial x, partial v, partial x, partial v, partial x. You can solve for each one. So this one is saying multiplying the first equation by 4. Then we have 4 partial v, partial x. Then minus this one. So this equation, so this becomes 12. This becomes negative 4. So subtract these 2 equations, we solve, we get a partial u, partial x equals negative 1/3. Okay, that's the example for the theorem. So inverse function theorem. So a special case of this general one is inverse function theorem, right? Jacobi determinant. Okay, this turns out to be important when we go to chapter 6 or chapter 5. So just a simple Jacobian determinant of f. Jacobian determinant of f. We use this notation or this partial notation. What is it? It's just calculating this matrix, right? This matrix, this n by n matrix. the determinant of this n by n matrix. Okay, inverse function theorem. We're working with the open set. Okay, f1 up to fn are real value functions from n space to 1 space, have continuous partial derivatives. So consider equation 4, this one, near a next point, x naught, y naught, which can be the solution of the system of equations. If the Jacobian, the n by n matrix is not 0, then equation 4 can be solved uniquely. It's a huge deal if we can solve uniquely the system of equations as x equals g of y, right? Inverse function, inverse. For x near x naught, y near y naught. Moreover, function g has continuous partial derivatives. Let's see this example. We have this equation, u defined in terms of xy, and v defined in terms of x and y. So u, v are functions from 2 space to 1 space. So near the point xy, can we solve for xy in terms of u and v? Oh, let's see. So let's think u as f1 in the equation, in the in this, because we're using this. So u as f1, v as f2, and we want to know near the points near, we can solve for xy as a function of u and v. According to the inverse function theorem, we must first compute the Jacobi determinant, right? Cannot be 0. So which is a 2 by 2 matrix in this case, because we have partial f1, partial x, partial f1, partial y, partial f2, partial x, partial f2, partial y. So then we call this a Jacobian of f. You just use capital letter J of f to represent. So we calculate, we get a function in terms of x and y. So at the point which this does not vanish, which means as long as this not turn into 0, we can solve for x and y. We can solve for x, y in terms of u and v. All right. In other words, we can solve for x, y near those points of x, y for which x is not 0 and this doesn't equal to this. So when you solve this, right, because basically you set this one to be 0, you see what can you solve? When you solve, you're saying if x cannot be 0 and this one cannot be this one, then we can apply implicit function theorem, so we can solve x and y in terms of u and v, because u and v are functions in terms of x, y. And if we can solve x and y in terms of u and v, that means we can find the inverse of x, inverse of y in terms of u and v. Okay, so this just for you to know, and will not be on the exam, all right? But you can try some, if you're a math major, you're a scientific major, science major, you should try to do some questions from this chapter. All right, now this, yes, any questions?
When I do the homework like 3.2, I have a little question. Like with the exercise question number 4 at 3.2, can you go over that question, please?
Yeah, let's go there. 3.2. Can you tell me which page?
I think it's page 166.
166. There will be one part of 180 something. Oh, this is 3.1. 3.2.
Oh, 193. Brian says 193.
Yeah. So question 4?
Yes, please.
All right. So the question is asking, in each exercise 3 to 8, determine the second order Taylor formula for given points x naught, y naught. So number 4, just this. Can you tell me what is the second order Taylor formula?
Like the formula I got is the f of x naught y naught plus the f of x naught y naught times the x minus x naught. And
No. Don't read it. Just tell me in language, in English.
like
Don't read it. Because for mathematics, if you read, doesn't mean anything. Just see what it is.
like
Second order.
second,
So first,
like the second derivative of the f of xy.
you involve that, right? So first you have to evaluate the function value at the given point. So f of 0, 0, that's the first part. Second part is the linear one. It's the first order Taylor formula. Do you remember what that is?
No.
That involves the first derivative, right?
The second and the first.
Right. If it's the first order that involves the first order derivative, you have to take a partial f, partial x, partial f, partial y, right?
Yes.
Then the second order, you just have to involve a second order derivative. Partial square f, partial x square, partial square f, partial y square, partial square f, partial x, partial y twice. I don't know what could be your question for this. This is very, very basic.
Like I'm trying to like solving the final answer for that. Like I was trying to but like I'm not really sure what's the final answer for question number 4.
The final answer could be anything. It could be a function in terms of x, y. Right?
Oh, so
because
it doesn't have to be the volume of that, right?
What do you mean volume? What does this to do with
Like
volume?
the number. Like
number, what do you mean?
I thought like as a question we did before, like there's all the final answer would be like numbers, like not the variables that has, or maybe the equation. So I just heard that you said
No,
it
it
could be
depends.
like anything.
It depends.
Oh.
No, it depends. It could be anything. It could be a number, which means it's just a constant function. Or could be a function just in terms of x, or could it be a function in terms of y? Depends on the first order derivative, second order derivative.
Oh, I see.
Could it be linear? Could it be a linear function? Could it be a quadratic function? It just could be anything. It doesn't have to be a number.
Yeah, that's why it confused me also. Yeah, thank you, Professor. I thought I got the like totally different one.
It's very similar to a single variable calculus. Right? Single variable calculus, when you do second order Taylor formula, it just could be at the most a quadratic function. Right? Or at least a number. It's just in between. It could be 0, could be a linear function, could be a quadratic function. In this case, the same thing. You could have a right, because specifically you involve. All right. Okay. Any other questions?
Actually, I have another question if possible.
Yeah, go ahead.
And there's sorry, give me 1 second. It's the 3.4, but I don't know what page it is now.
Which number?
That's the section 3.4 that with the example 6.
Example 6. Oh, example 6, not homework.
And not the homework. Like I was a little confused that like it says the solution pop up here, like the gradient f.
Okay. Well, here, which part?
The second part here. it says like the y, it could be like the gradient f of x comma y equal to y comma x. Like how can we switch that, like switch y and x position? And it says like y
Are you
equal
talking
to 2 lambda x, y, x equal to 2 lambda y. Yeah, that's the equation. Like I'm confusing of like the.
Oh, you're confused with this equation.
Yeah, the gradient f of x comma y equal to y comma x. Like why should we like in which condition we have to like switch the position?
Okay. No. Look at the gradient f of y. What is the gradient f of y? What's the gradient of f?
Oh, it's like a partial x equal to y partial x. Oh, okay. Never mind.
Okay. All
Yeah,
right.
so,
Any other questions?
yeah, so
Yeah.
the x could be the y and y could be the x, so we can slice.
No. It's nothing could be. What is gradient f? Can you tell me what is gradient f?
Like partial f of partial y, I mean partial f over partial x equal to y. And the partial f over partial.
I'm asking you gradient f. What is gradient f?
The first derivative?
Partial f partial x, comma, partial f partial y, isn't it?
Yes.
What's partial f partial x? That's y.
Equal to y.
That equals to y. What's the partial f partial y? That equals to x. There's nothing could be. In this example, that's exactly gradient of f.
Okay.
Y x.
No, I got it.
Right?
Thank you, Professor.
Okay. You're welcome. Okay, anybody else? Let me see the comment. We don't have to submit homework for 3.5 until August 7. August 7, the day we take our exam, right? Hopefully by then you finish everything. Oh, you don't have to. 3.5 is optional, right? You don't have to do it. Submit the homework too on Monday and realize you made a couple of mistakes. Nope. Don't worry about it, okay? No, because I don't want to create another one, resubmission for homework too. It's gonna be the list going to be too long. Not to worry, but it's good. You know, when you review, you find you made mistakes. All right, because homework is not like an exam. You know, I want your homework to be perfect, to give you full credits. No, I want to see how much you understand the material, and also you have to submit your homework promptly. But anyway, so this is summer session and everything. Right, homework 1, 2, 3, all postponed to August 7th, the day we take our exams. All right, any other questions? Otherwise, you're a free bird. And tomorrow, when you still have questions, we can still talk about to prepare you for your midterm. Right. If you don't have a question, you're a free bird. If you do, I'm here. Oh, thank you. Thank you for asking questions. Thank you, guys. Let me